All right, in the last video, we proved that span of S and span of T are equal if and only if these two conditions hold. S is inside span of T and T is inside span of S. So I want to show you what that implies, what it entails in the following example. So we're going to look at a space of matrices, M2 cross 2, and we're going to look at two subsets. So consider S, which is a subset of two matrices, these two, and T, which is a subset of three. Show that S and T span the same subset, so we want subspace, so we want to show that span of S equals span T. That's what we need to show. All right, so by the theorem, we'll show that S is inside span of T. And we'll show that T's inside span of S. So that means that I need to write every element of S. So I need to write A1 and I need to write A2 as a linear combination. That's what the span of T is, linear combination of the elements of T, so of these three matrices. All right, so let's start with that. I'm going to take A1 to be 1, 2, 8 minus 1. I need to write it as A1 times the first matrix, so B, plus A2 times B2, so 1, 2, 1, 7, 1, and A3 times B3, 1, 1, 5, 0. All right, that's going to give me a linear system. If I look at the first entries, I need that 1 times A1, 2 times A2, and 1 times A3 equals 1. I need that 2 is equal to 0 times A1, 1 times A2, 1 times A3, so 0, 1, 1 equals 2. I need that 8 is equal to 2A1, 7A2, 5A3, so 2A1, 7A2, 5A3 equals 8. And finally, I need minus 1 to be equal to A1 plus A2. All right, that's the matrix I have. Let's use magic to reduce it. All right, I got minus 1, 1, and minus 3, 2, 0, 0. All right, so there are infinitely many solutions. That means there are infinitely many ways of writing A1 as a linear combination. I just need one. As long as this is consistent, I'm okay. So let me put that a bit slightly to the right. Slightly to the left, I mean. So here, this is consistent. I'm going to take A1 to be minus 3, A2 equals 2, and A3 is going to be 0. So any solution works. This is one of them. All right, so I'm getting that A1 is minus 3B1 plus 2B2 plus 0B3. So it is in span of T. All right, so matrices are a lot like vectors. They're just written slightly differently, and we have a weird product. So one thing I want to show you is how the matrices relate to my system. All right, so the first matrix I have here, let's do it in yellow. The first generator here, 1, 0, 2, 1 ends up being the first column. You just have to pick a way of going through your matrix. As long as you're consistent, it's going to work. So here I have 2, 1, 7, 1, 2, 1, 7, 1. Then I have 1, 1, 5, 0, 1, 1, 5, 0. And I want to get from this, I want to get 1, 2, 8, minus 1. 1, 2, 8, minus 1. All right, let's try this for A2. A2 was 0, 1, 3, minus 1. I want to write it as A1 times 1, 0, 2, 1, plus A2 times 2, 1, 7, 1, plus A3 times 1, 1, 5, 0. All right, so let's do the same thing. I'm going to put the first matrix here, the second one, so same as above, but now the constants are 0, 1, 3, minus 1. So again, same yellow, same orange, same red, but now let's use blue. This one is slightly different. All right, again, you reduce, you hope that the system is consistent. I'll get the same coefficient matrix because I started with the same coefficient matrix before reducing. I get minus 2, 1, 0, 0, so it's consistent. And I could take A1 to be minus 2, A2 to be 1, and A3 again 0. So A2 is minus 2, B1 plus B2 plus 0, B3. As long as you find a linear combination, you get that it is inside span of T. All right, so we have shown that both elements of S are in span of T, so S is a subset of a span of T. Let me give you a trick. I mean, you're going to need to do something like this on the assignment, and so you can actually solve both at once. So I'm going to take, my yellow matrix, my orange matrix, and my red matrix. So these are the same for both A1 and for A2. So since I have the same coefficient matrix, what I could do, that's going to remind you of when we found inverses. So I had 1, 2, 8, minus 1, and 0, 1, 3, minus 1. I'm going to solve both by just putting the constants next to each other. And if I reduce, I'm going to get the solutions next to each other. So I'm going to get minus 3, 2, 0, 0, minus 2, 1, 0, 0. All right, so you can do both at once. All right, we've proven that span of T contains S. That's the first part. We need to prove the opposite. So now that we've written the A's in terms of the B's, we have to do the opposite. We have to write the B's in terms of the A's. All right, so that's going to be part 2, hence the second page. So we want to show that T is inside span of S. So we need B1 equals A1, A1 plus A2, A2. B2, let's use different numbers. And B3, C1, A1 plus C2, A2. All right, so I'm going to use the trick. I'm going to put A1 and A2 as my first two columns. So the first one was the purple one. Second one was the blue one. So my first one was 1, 2, 8, minus 1. The other one was 0, 1, 3, minus 1. And then I'm going to put B1. I'm going to put 1, 0, 2, 1. I'm going to put B2. And I'm going to put, what's B3? 1, 1, 5, 0. All right, so I'm shifting what is the constants and what is coefficients. All right, and I'm going to reduce this. I'm going to get 1, 0, 0, 1. And I will get 1 minus 2, 2 minus 3, 1 minus 1, And so B1 equals, so that, sorry, that orange column gives you the coefficient for B1, as long as it's consistent, so all three consistent, because I don't have anything non-zero in the bottom two rows. So B1 is 1A1 plus minus 2A2. B2 is 2A1 plus minus 3A2. And B3 is A1 plus minus A2. And so yes, T is inside span of S. Since we have S is inside span of T and T is inside span of S, theorem 1.3, sorry, 1.3.2 tells us that the span of T and span of S are equal. All right, that's it for now. Next video, we'll be starting a new chapter. We'll be talking about linear dependence and independence. That's really to say, if I start with two vectors, will I get a plane, or are the vectors redundant? All right, so we'll be generalizing what we did for our n in linear one.